So previously we had learned how to find intervals of increasing, decreasing, and local extrema graphically. Now we're going to do the same thing but given a function, so we're going to do it analytically. So first thing, we know that we need to find our critical numbers. So given a function, step one is to go ahead and find our critical numbers. So my derivative is going to be, bring down the 3, so this is going to be x squared minus 1. We want to find where the derivative of 0 does not exist. And there's no places where it doesn't exist, but I can factor this. So my critical numbers are x equals 1 and negative 1. Okay, so now what we're going to do is we need to figure out what's happening on the intervals before and after these critical numbers. So we're going to set up a number line very similar to how you did key numbers in pre-calculus. So, and we're going to use these critical numbers to split up this number line. So we're going to use negative 1 and 1. And what we want is we want to find the sign of the derivative. So we're always using the derivative to give us information about the original function. So we're going to go ahead and test these intervals. So I'm going to plug in a number to the left of negative 1, and I'm going to plug it into the derivative. So you can plug it in here, or plug it in here. And I don't care what the value is, I just need to figure out what the sign is. So if I plug in negative 2 and plug it in here, that'll give me a positive 3. So this number is going to be a positive number. No matter what number I pick to the left of negative 1, if I plug it into the derivative, it will be a positive value. If I plug in a value from negative 1 to 1, 0 is easy to plug in. I will get a negative value. If I plug in a number to the right of 1, such as 2, I'll get a positive value here. So this is telling us that from negative infinity to negative 1, the sign of the derivative is always going to be positive. And remember we learned previously that f prime positive means that f is increasing. Or you can draw an arrow instead. F prime negative means in this interval the function is going to be decreasing. Or you can draw the arrow showing that it goes down. And again, f prime positive means that the function is increasing. Okay, so first thing I have from here is I can find my intervals of increasing and decreasing. So based on my information from my number line, I know that it is increasing from negative infinity to negative 1 and 1 to infinity. You don't need to put a union symbol. You don't need to put anything in between. Parentheses are fine everywhere. And notice it says justify your answer. So your justification or your reasoning is because we figured out that f prime of x, the derivative is positive. And then decreasing, same analysis. We know that it's decreasing from negative 1 to 1, and your justification is because the derivative in that interval is negative. Okay, so that's my increasing and decreasing. Now, next thing we're going to do is we're going to find actually all our local extrema. So not absolute maxes and mins, but local maxes and mins. So remember, local maxes and mins can only occur in the interior of the function, so we don't care about the endpoints. There are no endpoints here anyway. And it could only occur where you have critical numbers. So these are your only possibilities here. Now let's look at what we just found out from here and see what's happening. The original function is increasing and then decreasing. So that means right here there has to be a local max that's happening. And then from here the graph goes from decreasing to increasing. So right here is a local min. And the way that you show your answer is you're going to tell me that your local max, and we always want the y coordinate, occurs at f of negative 1. There's my local max, that's my x value, but I want the y value. So we want to take the negative 1 and plug it back into the original function. So if I plug in negative 1 into the original, you're going to get negative 4/3 as your y value. Your justification is because we figured out that the derivative was 0 and the sign of f prime changes from positive to negative. So all you're doing is really restating what we have on this number line. And then we're going to do the same thing for local min. We have f of 1 equals negative 2/3, and your justification is because f prime of x is equal to 0 and sine of f prime of x changes from negative to positive. Okay. Once you pause the video at this point and try B on your own, and then come back and replay the video to check your answer. Okay, so let's do the same thing for this one. So f prime of x is 3x squared plus 2x minus 5. We need to find our critical numbers. This actually factors nicely, 3x plus 5, x minus 1. So x equals negative 5/3 and positive 1 are my critical numbers. I'm going to set up my number line. I need to use negative 5/3 and 1. Label your sign chart. I need the sign of the derivative. So you're going to plug numbers into the derivative, but that's going to give me information about the original function. So if you pick a number to the left of negative 5/3, the sign of the derivative is always positive. This is going to be minus, this is positive. So check these signs for yourselves. That means that on the original function, the graph is increasing, then decreasing, increasing. So very similar to the problem that we did above. Okay, so now let's summarize our answer. So increasing from negative infinity to negative 5/3 and 1 to infinity, justification is because the derivative is positive. Decreasing from negative 5/3 to 1 because the derivative is negative in that interval. Notice I have a local max at f of negative 5/3. Take this, plug it back into the original function, and I'm going to round it off to 4 decimals. Because the derivative is 0 at that point, and the sign of the derivative changes from positive to negative. Okay, and then we also have a local min at f of 1, which is going to be negative 8, because the derivative is 0, and sign f prime changes from negative to positive.